So next we'll talk about the power flow solvers. There are several power flow solvers used in Gridlab-D. The first and simplest one is the forward backsweep solver. Some people refer to this as Kirsting's method, since I think it's described most thoroughly in his book. And this book was actually used as the primary guide to implementing the solution method in Gridlab-D. It's a really efficient solver. It works very quickly, but unfortunately it works only on radial systems. It won't work on network systems. I should point out though that when we say radial systems, it means a system that is physically actually radial, as opposed to, let's say, a network which has open closed switches. So if you have a network where the switches have been opened such that the system appears to be physically radial anyway, you can use a forward backsweep solver and it will work correctly. But if you were to close any of the switches and create, for example, lateral flow between two radial branches of the network, then the method won't work correctly. There are also some objects in the power flow module that do not work when you use forward backsweep method. So there's specific types of equipment that will raise an error if you try to use the forward backsweep technique. There are also some solution methods and analyses that don't work with forward backsweep. In addition, I think there are also some faults that don't get handled by the solver. So in any situations where forward backsweep method is not appropriate, you'll get a warning that says that you should not be using that solver and you should switch to the Newton-Raphson method. So the solution algorithm is really straightforward. Essentially, as you sweep down, you update voltages, and as you sweep backward, you update currents. And then the values that are used for the updates are basically matrices that are developed for each of the links and nodes of the objects in the network. So really, the only thing the algorithm has to do is set the ranks appropriately. And then what ends up happening is the sweep up and down will update the currents and voltages in the correct order, hence the efficiency of the method. It's particularly efficient because it does all the other updates of objects within the same sweeping process, right? So we've talked about how the main core solver does these pre-sync and sync events, and that's when, of course, it's doing these calculations on the voltages and currents. But the objects themselves are also being updated at the same time. And so what ends up happening is that the updates of currents and voltages, because they're happening concurrently in the main loop with the updates of other things like loads and controls and such, that means that there's only one loop sequence that's being processed up and down through the objects, not multiple loops that are disconnected. And this results in a pretty significant performance benefit. But as I said, the forward backsweep method has limitations, and to address those limitations, there's the more general Newton-Raphson solver. So this solver is not as fast, but it is much more robust, and it can handle a wider variety of conditions. The other thing that's really interesting about the way the Newton-Raphson implementation works in Gridlab-D is because Newton-Raphson has to start from some initial condition and then iterate towards the solution, it chooses to use the last steady state as the initial conditions for iteration towards the next steady state. And most of the time, the last steady state is really, really close to the next steady state. I mean, if you think about it, right, you've got loads that are changing, but they don't change a lot. They typically change just a little bit from one steady state to the next. And so those small changes mean that the Newton-Raphson solver can usually find the next solution in one iteration. And so only if there's a major change in the network, in the loads or the topology of the network, or the boundary conditions at the top of the network, only then would it have to iterate more than once. So generally, the longest solution is the very first solution, when it has to start from a cold start and it doesn't know the initial conditions. If you give it pretty good initial conditions, you can even make that one go fairly quickly. So this Newton-Raphson solver is quite flexible, and really good for all the various configurations we might find in networks. One of the things, though, is that the Newton-Raphson solver may fail to converge on a variety of conditions. Typically, these are associated with excessive load or excessive generation. It can also happen as a result of bad configuration of a link, like a line that has bad properties or things like that. One thing to be always aware of is that failure to converge does not necessarily mean that this network is infeasible. It simply means that the numerical methodology doesn't work. I think there's often some confusion that because we can't solve the network, that means the network actually isn't a feasible network, or vice versa, that infeasible networks are necessarily not solvable. That's not true. And so, for example, we can find solutions that have pretty extreme voltage conditions, far more extreme than you would ever find in real life. And conversely, we can find situations where a perfectly reasonable voltage levels on the network can't be solved. And it just has to do with the numerical method itself. It has nothing to do with the properties of the network. Intrinsically, a different solver would presumably be able to find the solution. It's just that the iteration method and the overall algorithm may come up short given the properties that we've provided in the model. So this is not uncommon to see convergence failures, and the methods for dealing with convergence failures are fairly typical. Look at the voltages, look at the currents, try to identify which node or which link is causing, or there may be more than one, but which one is causing the difficulty for the numerical method, and correct that one. So the overall method is basically to solve the real and reactive current injections, and use those to update the voltages. So it's a pretty straightforward description of the method. The implementation, of course, is quite detailed. There's a lot going on. For those of you who have the privilege of working on it, there's a ton of moving parts in this thing. Each object has its own way of calculating its contributions, and then the actual solver itself is quite sophisticated. It has many performance enhancements embedded in it. So there's a lot going on, but it's quite powerful. The other thing to keep in mind is that the internal solver uses super LU, but you can link an external LU solver, and in fact there is one that's been prepared using a solver called KLU. KLU is known to be a bit faster than super LU, but it comes under a different license that can't be delivered with Gridlab-D. I think it's a GPL license. So you have to sort of build it and load it yourself. And of course, it also illustrates how to create your own solver, which is really amounts to defining these four functions. And the KLU solver is a good example of this, and you can go and look at how it works. But you have to basically provide this data and implement these four functions, and that allows you to link an arbitrary solver of any kind in place of the solver that's used in the Newton-Raphson method that is provided with Gridlab-D. So that's just an interesting aside. And I think for developers, it's something that is an opportunity to connect different methods and perhaps improve the performance further. The other part of Gridlab-D that's included is the machine learning enhanced power flow solver. So this is a solver method that uses an external predictor that attempts to solve the network flow problem that's given before giving Newton-Raphson the opportunity to solve it. And if the solution appears to be good, the estimate, the predicted solution, is provided back to Gridlab-D. But if it's not sufficient, then the Newton-Raphson power flow solver is run, and the solution obtained from Newton-Raphson is given back to the predictor as a learning opportunity. So the overall methodology is essentially to use this approximation method in cases where the solution is very close to an existing solution. So you can think of this as a form of linearization about the most recent solution found from the Newton-Raphson solver. And of course, this ability to linearize in the neighborhood of a good solution can result in really significant performance improvements. And so this is how these methods work. So the way you link a machine learning solver is using the solver.py.conf. So this is essentially configuring the Python link to the solver. You specify the path to the solver, the file name that implements the solver, what information is passed to and from the solver, and the learning component of the solver. And then there's this component here called the topology hash resolution. So any change in topology of any significance would result in a change in a hash code. The hash code is used to detect whether a significant topology change has occurred that might affect whether the current solution being used is the correct one, and perhaps even allow a learning engine to maintain multiple solutions for different topologies. So let's say, for example, we have a network that has one configuration, and the learning solver learns that configuration pretty well, and then we change configuration and can no longer use that one, and it begins learning a new configuration. Well, it remembers the old one, and if at some point down the line in the simulation, the old configuration is restored, using the topology hash would allow you to recover the model that you had saved from the previous topology and begin using it again, so that the system can learn multiple topologies and keep track of them and switch back and forth between them in order to avoid having to relearn a new topology every time something changes. And the last item is just a shorthand, enables a more efficient data transfer method, but that's not relevant to most general learning enhanced solvers. So the basic algorithm is this. When we go to run a power flow solution, we first run the learning enhanced solver, and if it succeeds, we return that solution. If it fails, we run the Newton-Raphson solver, and of course, if that solver fails, then we don't have a solution, and that we just tell Gridlab-D we're done. We can't solve this problem. But if it succeeds, we hand that solution to the learning module, learning component of the MLE solver implementation, and then we return the solution that was found. So this ability to try and then learn from failures, I think, is an important addition to the overall methodology, and it creates the ability for us to implement a wide variety of learning methods based on the experience developed running a simulation for a model. So if you're running a simulation over a very long time span, this can have a very significant impact on the performance. If you're running a short duration simulation, probably won't have much effect. It doesn't make a lot of sense to use this because there probably won't be enough time to learn enough configurations or get enough data about different solutions to be able to apply that effectively and enhance performance. But let's say for annual simulations, this makes a lot of sense and it can be pretty effective. So here's an example of the bus data that's available to a learning solver. Basically just all the information that's given to the Newton-Raphson method about buses. And all of this can be looked up in the documentation to the Newton-Raphson implementation itself. The header files has all the documentation. It's all available in the technical documents generated when Gridlab-D is built. Similarly, branch data, there's not as much branch data, but this is all the data that's handed to the Newton-Raphson solver when it needs to solve a network. And then the learn data is everything that you would pass to the learning module in addition to the bus and branch information. And so this is basically everything that comes back from the Newton-Raphson solver that might be of some use in learning. So, you know, the Y matrix and some of the other information related to the solution. And so overall, this information is everything that is needed to both solve and learn from solutions using a Newton-Raphson method. All right, so here are the two implementations that have to be provided in Python to implement a learning solution. The first is the solver itself. And if the solver succeeds, it returns a positive or 0 value. If it fails, it returns a negative value. And then the learning component, which has no return value. So that's not, you know, it's not important that it actually succeed in learning. The main solver ignores the result of the learning process. So that's basically all there is to it. You know, obviously implementing a solver requires fairly good knowledge of how these data structures work and you know, what are the primary features that are relevant to the method that you're using for learning. That is all a subject of another time and another session, and we won't get into that for this session. It's quite different from what you would normally do in a PowerFlow solver, and we will leave that to some other time. Okay, so now let's talk about how we solve for specific objects in Gridlab-D. So let's start with links and specifically line properties. So all the line properties are calculated from the configuration objects for lines, and we've talked about those before. I should point out that it is possible to create a configuration that gives rise to negative impedances. And in fact, some of the test models do in fact, they do have those. And you'll see warnings when you run those networks about it possibly giving unexpected results. Typically, you should fix those, should not leave those in the networks. It's not always obvious what gives rise to them, but it can be things like spacing or radii that are not appropriate, or you know, things like that. So not the easiest thing to address unless you know how these line configurations are calculated. Another thing to be aware of is that shunt admittances are not included by default. You can enable them for a module, for the entire PowerFlow module, by just setting the global line capacitance equals true, and that takes care of including them. But just bear in mind that they're not there normally. Another thing to keep in mind is that secondary lines, the triplex lines themselves, use a different object because their phases are rearranged. The lines are actually arranged as line 1 neutral, line 2 with voltages of negative 120 volts, 0, positive 120 volts. So the angles are 180 degrees out of phase with each other with respect to the phase that they're connected to. So, you know, obviously if it's connected on, you know, phase A, it'll take the 180 degrees plus or minus across phase A, versus if it's on phase B, it's 180 degrees plus or minus relative to phase B. So that's just something to keep in mind about how triplex lines work. So the configuration for overhead lines includes the radius, the geometric mean radius of the wire itself, the resistance of the wire, the diameter, and so on. So there's a lot of information is derived from these properties, as well as the continuous ratings, which are used to detect things like current violations and current limits when using, when enabling those in the PowerFlow module. So if you exceed those ratings, you'll get warnings or possibly even a violation if you enable detecting violations. Line spacing is pretty straightforward. It's basically just the line to line and line to neutral and line to earth distances that need to be included for all of these in order to calculate the line properties correctly. Not much to this other than getting them right. But most line configurations are pretty straightforward to model, so this is not generally a challenging thing to get correct. Underground lines do require quite a bit more information than overhead lines. And so you can see here all the information required relating not just to the line itself, but also the neutral, the relationship of the lines in the neutral, insulation and shielding and so on, as well as the rating limits also included in this line as well. Which will be checked if ratings are checked during this power flow solution. So here's a little bit more detail on triplex lines. As I said, the conductor information is a little bit different. Triplex lines do have insulation, and so you have to provide that information. You can, of course, just provide all of the Z matrix directly to the lines. And this option is always available. So if you are just importing impedance data, you can do that. You can also use it to fix bad impedances if you want. This is used, essentially, this can be used to overwrite information that was developed from these other properties if you need to do that. All right, so for transformers and regulators, not all transformers types are modeled, but the most common ones are. And so these are all listed here. And in particular, the single phase center tap transformers that are used to convert from a 3-phase to a triplex configuration, those are covered. All of the models, transformer models, use the standard American 30-degree connection, that does the 30-degree phase configuration. So that standard is implemented entirely in all of these. And then for regulators, they're essentially the same as transformers, but they have different control modes. The default mode is manual. So there are 3 control modes. One is a remote node, where you have you're essentially monitoring another node in the network. And then based on the status of that node, the regulator will change its state. And then, of course, 2 other control modes: output voltage, which is the output of the regulator itself, and then line drop compensation. When you're using line drop compensation, you do need to provide additional information for the line drop compensation calculations. The impedance information, as well as the phase, the information for each phase. All the controls require you to set the band and the dwell, so the band center, band width, and the dwell time, as well as possibly the limits on the taps. And then based on those, you'll see the tap positions change over time from what they would have been set initially. If you're using manual, the tap position remains unchanged. You have to change it yourself, which you could perfectly well do either from SCADA data or from some external control strategy you want to impose on the model. Again, using Python, this is relatively straightforward. So for transformer configurations, you can specify the different connection types, which relate to what we saw earlier, as well as different installation types. And then there are a lot of other properties as well. And you can get all of those properties from the module description for transformer objects. I'm not going to go into much detail on all the other properties. There are some very interesting properties that are useful for transformer aging studies. So I'll just briefly mention those here. They do require that you connect the transformer object to a climate object. And so that you'll have to specify the weather conditions it's exposed to. But that will then allow you to enable a thermal model that uses the power loading on the transformer and the overheating of the transformer itself to calculate possible loss of performance in the transformer. Okay, so for loads and meters, three-phase, so I'll make a distinction between three-phase loads and meters and triplex loads and meters. But for three-phase loads, they can be connected either as Y or delta. And so the power values are taken directly from the load according to the phases, and then the current and impedance values are calculated using the standard voltage response. And in the case of meters, this information is then used to calculate the interval energy, which is basically just the power multiplied by the power magnitude multiplied by the time. So this is all pretty straightforward, and you know, shouldn't come as a surprise to anyone on how it's done. There is a special load called a PQ load that allows you to create loads that have sensitivity to weather conditions. And so there's a set of parameters. It's quite a large set, actually, because it's a combinatorial thing where you can specify the impedance, current, or power, real or reactive response to temperature, humidity, solar, wind, and rain, all independently, each one separately. I should point out the real and reactive actually only apply to impedance and power. The current is magnitude and angle. It would be ZPQT or ZPT, for example, which would be the constant impedance real power response to temperature. But you would find that current would be IMT. It would be the current response magnitude to temperature. So they're grouped. It's a little misleading when you look at the way this is documented, but they actually correspond differently. And then, of course, you can specify all of the input values. So the input temperature, humidity, rain, wind, and solar. And then, of course, all the output values, the output impedance, current, and power. And again, real and reactive impedance and power, and then magnitude and angle current. And so those are the PQ load. This gives you the ability essentially to construct loads with any kind of response structure, arbitrary response structure, without knowing exactly what's happening behind the scenes in the physics. So you can construct your own real and reactive power models based on temperature and basically based on all of the weather. Okay. For switches, fuses, and relays, these are used to change the topology of the network. And so obviously the main effect of these is a change in impedance. When a switch or relay or fuse is closed, it has some very, very low impedance. And when it's open, it has an infinite impedance. Most of these are controlled by phase. Switches in particular can be controlled individually, or they can be banked so that controlling one phase controls all the phases. But I believe the default is that they're individually controlled. And so you can have a switch that turns on and off each of the phases separately on each of the lines. And then, of course, with relays, the relays are essentially operating reclosers, and these reclosers have a delay time before they retry, say 5 seconds or so, and they have a maximum number of retries. If after that number of retries, the relay can't be closed successfully, then the recloser locks out and remains locked out. I forget how long it remains locked out for. Actually, that's a good question. I believe it does eventually reset, but I don't know how long that is. And then fuses are essentially overcurrent, and right now the current limit is very high. And then it has a mean replacement time. Typically, the default is 1 hour. The resistance to the fuse does have to be provided. And that's, of course, the resistance when it's good. When the fuse is blown, the impedance obviously goes to infinity. And then the fuse status is given by phase. So you can define a three-phase fuse, but it will actually model the individual fuses on each phase separately. And so when a fuse is blown, you'll see its status change on the line, on the phase on which it had to, where it saw the overcurrent. Okay, for capacitors are fairly straightforward to implement. They have a switch status where you can bring the capacitor in and out of service, and the phase that participates in the switching control scheme and the phases to which it's connected. And then, of course, it keeps track of the number of switching operations that it has seen, the number of changes from open to closed and closed to open. And this is used to determine whether there's excessive capacitor operation resulting, say, from highly intermittent renewables or something like that. Here too, there are multiple control strategies available. Manual is the default. You can have volt control, VAR control, and VAR volt control. So all of these are available, and those are done. I believe they're done as given the voltage at the terminals. I don't believe there's a remote node associated with those with capacitors. There's also a special volt VAR control strategy that's implemented. So there's an object that actually will operate those and allow you to configure much more complex control strategies for coordinating capacitors and regulators to minimize losses. And so those are much more, this is a much more advanced control strategy that's used for managing voltage. All right, so for substations, the substation object really does two things. One is it generally serves as a swing bus or the RIT bus for a forward back sweep. You don't have to use a substation. You can just set up, for example, a node on the primary side of the feeder transformer, the load tap changer, and not implement the substation. The advantage of implementing a substation, the primary feature, is that it can convert the unbalanced network that you have in your distribution system to a positive sequence model that can be used to connect it to another solver that might implement the subtransmission network itself, where the expectation is that the load is more balanced. And so it's really just a matter of performing these conversion calculations to get the positive sequence model. And then those voltages are available for use with other solvers. So that's the basic idea. Yeah, it's pretty straightforward. I think the other thing that can be included is the frequency, the reference frequency for the system. But because the frequency is uniform throughout the distribution network, or at least through all the connected components of the distribution network, that's a trivial matter. Just for your information, there are a number of other power flow objects. We mentioned them earlier. The fault check object is used to enable fault verification. So, line-to-line contact, line-to-ground contact, vegetation to line contact, things like that, or other kinds of failures of equipment that would cause the topology to change, or elements of the network to go out of operation. So check mode is what you use to enable it. Output file name will record the fault events. Reliability mode turns on the reliability metrics associated with fault detection. And then grid association is used to enable islanding operations, so that when a fault occurs and say a switch opens a section of the network, we might be able to isolate parts of the network. This is primarily used for reconfiguration and restoration strategies where you can isolate sections of the network and end up with two different networks that operate independently, let's say with a lateral or something like that. Another object that's available is a motor object. The main use of the motor object is in delta mode, so we generally don't bother with them in steady state because they're easy enough to implement as part of the load models anyway. The primary purpose of the motor model is to implement stalling behavior and back generation and things like that. As I said, the restoration object handles reliability. So when you enable fault checking, you can use the restoration object to perform reliability analysis. A couple other objects of interest, there's a series reactor, and it's a pretty straightforward concept. Sectionalizers, which are used to coordinate relays. The power metrics themselves that generate the SAIDI, and KFE values that you use to evaluate reliability. There's an emissions object that generates emissions data related to the loads on the system and what their greenhouse gas emissions would be. And there are various dump objects that are used to generate voltage, current, and impedance dumps, as well as a billing dump for triplex meters. So if you provide a file name, a run time, basically how often do you want the dump to be done, and run count, how many times will you allow the dump to be done, then you can specify a voltage dump that will allow you to diagnose whether you've got a problem. If you're having a convergence problem, for example, voltage and current dumps can be very useful, impedance dumps as well. They can help you identify where the source of that problem is by inspecting the dump and looking for very unusual voltages, currents, or impedances. So that's overall basically everything on the power flow solver itself and how it works. So at this point, I'm going to stop recording and open it up to questions.